Welcome to the third video lecture of the lithography tool package training at DTU Nanolab. This lecture is a more detailed look into the exposure process. At the core of the lithographic process is the transfer of some kind of pattern onto some kind of substrate. Since most substrates used in semiconductor fabrication cannot usually be patterned directly, we instead transfer our pattern into a photosensitive polymer film, and in later process step we can then transfer the pattern from the film into our substrate. In broad terms, we have three different types of photoresists, two of which are not technically photoresists. The resists are made for specific radiation types, which is what defines the resist type. We have resists that are sensitive to photons, which are correctly called photoresist. These are used for photolithography, which is the backbone of the entire semiconductor industry. Then we have resists that are sensitive to electrons, which are called electron beam resists. E-beam lithography is used for producing the smallest features possible, but is often a more expensive and slower process than photolithography. Finally, we have imprint resists, which are resists that are not necessarily designed for radiation sensitivity. Imprint lithography instead uses stamps to mechanically deform the resist. The imprint stamp is often made using e-beam lithography, and produces features with the same high resolution, but at a much lower cost, since stamping is often quite fast, and once a stamp is made, it can be used many times. All three types are often referred to as photoresists, even though it would be more correct to only use that name for the photon-sensitive resist. When talking about exposure as a lithography process step, imprint lithography is not normally part of that talk, since it technically does not expose the resist to radiation. Imprint lithography is mentioned here because it is a method of pattern transfer, but for the rest of this lecture, only radiative exposure methods will be used as examples. The exposure always requires some sort of pattern masking method. For some tools, this pattern mask is a physical shadow mask, which works by blocking parts of the exposure radiation. The unblocked radiation will then proceed through the mask to interact with the resist and cause some kind of chemical reaction, which leaves a latent image of the pattern in the resist. Other tools do not use a physical shadow mask. Some of these tools instead use a digital mirror device, exactly like the mirror device in a movie projector, to act as a shadow mask, but a shadow mask which can be changed when needed. Other maskless tools use radiation beams to draw the pattern directly into the resist, just like you would draw with a pencil. Before we look at specific tools, we first look at the photoresist spectral sensitivity. It is important to know that photoresists are not uniformly sensitive to the light across the entire spectrum. In the graph is shown the attenuation coefficient for 4 different UV photoresists. This is a measure of how much light the resist absorbs at specific wavelengths, which is correlated with the photoactivity. Without going into details, we still see two very distinct features. First, we see that none of the 4 resists are identical. This means that you should not expect them to require the same amount of exposure radiation energy, also known as the exposure dose. The second thing we can see is that the sensitivity for any specific resist varies depending on the wavelength. If we look at the resist AZNLOF 2020, we can see that the sensitivity at 365 nanometer is quite high, but it then drops close to zero at 405 nanometer. The practical meaning of this is that it becomes important to choose the correct exposure tools. The exposure light source wavelength has to match the sensitivity spectrum of the resist, otherwise you may not be able to expose it at all. At DTU Nanolab we have a number of different exposure tools available. Each of the tools have processes they are good for, and other processes they are less good for. It is up to you, the user, to determine which tools best suit your process. We'd always recommend having your process evaluated by our fabrication support team. This evaluation essentially enables you to stand on the shoulders of those who came before you, without having to rediscover their mistakes. For UV processes we have a mask aligner which can be used for processes requiring the traditional mercury spectral lines, I, H and G, at 365, 405 and 435 nanometers respectively. This tool is normally set up to only output the 365 nanometer spectral line. We also have 3 UV maskless aligners which have exposure light at 365, 375 and 405 nanometers. Each tool only has a single wavelength light source. For deep UV processes we have a DUV stepper with a 248 nanometer light source. Our electron beam tools are technically not light sources but instead electron sources. We have 2 different E-beams available, an advanced tool capable of sub-10 nanometers resolution and a simpler tool capable of approximately 50 nanometers resolution. After finding the resist and exposure tool you want to use, you now need to determine how much energy you need to put into the resist. This is known as the exposure dose. If the dose is too low or too high, you will end up with artifacts in the pattern, or maybe it even becomes completely unusable. The dose is the product of how much power per area, in the light, and how long time the resist is exposed to this light intensity. Before you even begin your process, there are a few ways of getting estimates of what your dose should be. First, you can try to calculate it by looking at it as a physics or chemistry problem. This is probably the least good way, as it is a complicated problem to solve. Next best estimation is to look in the datasheet for the resist. Here you will often find dose values for specific film thickness using specific tools. This estimate is much easier to obtain than trying to calculate it, but will often only give you generic values for resist thicknesses that you may not use, or for tools that you are not using. The best estimate you can get is by looking at other processes run on the specific tool you want to use. If you can find processes that use the same substrates, resist and resist thickness, then you have a pretty good estimate of what your dose should be. Unfortunately, you cannot always be certain that the dose you find is going to be optimal for your project as well. Some projects are just different and requires different doses, even if they use the same substrates, resist and resist thickness. The optimal dose can sometimes be dependent on the exposure pattern, which is highly likely to be different for every project. The best method for finding the exact optimal dose for your own project is to run a dose test. This determines the precise dose for your project using your tool, your substrate, your resist with your resist thickness, as well as using your specific pattern. We always recommend users to run their own dose tests, using their own critical features as test pattern. After going through all the work finding your optimal dose, you unfortunately also have to sometimes repeat that work. Ideally, everything inside the cleanroom would be constant, but that is just not the case. Tool performance can change over time, or tools can outright break. Ambient humidity changes with the seasons, which can impact the resists as well as certain tools. The resists, and all other chemistry, can sometimes change slightly from batch to batch. Even the users themselves change from day to day. I'm sure you can imagine experience varying levels of stress leading up to finishing a project, or maybe you're just more tired today than you were yesterday. This could affect the way you do certain tasks. If you experience that your process results change, you may need to redo the dose test. The optimal dose depends strongly on the substrate type. A silicon wafer has different optical properties than a transparent glass substrate. It also depends strongly on the resist type and thickness, which makes intuitive sense as this determines the spectral sensitivity and absorption. Certain film thicknesses also introduce thin film effects, which affects the constructive and destructive interference inside the resist film. If you have other layers on the substrate, such as a layer of oxide or nitride, you change the reflectivity and absorption properties of the substrate. These thin film layers also introduce thin film effects. The optimal dose can also depend on the pattern being exposed. An example of this is that the optimal dose for a pattern of tiny dots may not be the same dose as it is for a pattern of optical grating lines. We always recommend users to run their own dose tests, using their own critical features as test pattern. The physical shadow mask is a square glass substrate, which has a pattern on one side. The pattern is made with chrome and the chrome is coated with an anti-reflective coating, which makes it look brown when viewed from one side. At DTU Nanolab we have 2 types of tools that use physical shadow masks. The first tool is called a mask aligner, which is a contact exposure tool. This tool uses shadow masks which are placed in contact with the substrate. Light is then passed through the mask into the resist, which leaves a latent image of the mask pattern in the resist, in a 1:1 magnification. The second type of tool is a deep UV stepper, which is a projection exposure tool. In this tool, the mask, which is now called a reticle instead, is placed far away from the substrate and light is then passed through the reticle. It then passes through demagnification optics, which shrinks the image by a factor of 5. Masks are made by sending a mask design pattern to a mask manufacturer, who then produces the mask. Digital masks are used in tools, which have some kind of mechanism for translating the design file into controlled exposure of the substrate. In our maskless aligners, the design file is converted into image files, which are then projected onto the substrate using the same type of digital mirror device found in ordinary movie projectors. This means that the maskless aligners actually still uses a sort of physical mask, just one that can be changed to any pattern almost instantaneously. Our other type of maskless tools are the electron beam tools. These are truly maskless. They work by focusing a narrow beam of electrons and then scanning this beam across the substrate. It works essentially the same way as a scanning electron microscope. Design files can be made using many different softwares. Some of these are free and open source software, while others are licensed at varying price ranges. We're now going to look more at the UV mask aligner and the UV maskless aligner. These are very commonly used UV lithography tools. Using the mask aligner is in principle simple, but requires some amount of technical skill. The first step is to load the mask into the machine. Then the substrate is loaded. The substrate and the mask is aligned so the position fits. This is where the name of the tool, mask aligner, comes from. When the alignment is acceptable, the exposure is started. After the exposure, the substrate is removed from the tool. When the entire process is finished, the mask is removed from the tool. The mask aligner is a simple tool. It is basically a glorified lamp. This means that it has very few failure points, and is relatively easy to learn to use. It also exposes the entire wafer area in a single shot, which makes it quite good for processing large batches of wafers that all need the same pattern. Some of the downsides of the tool is that it lacks some of the more advanced alignment features. It also relies a lot more on the skill of the user to get high alignment accuracy, since it is done manually. In order to get the best possible resolution, it is also required to have good physical contact between the mask and the substrate. This means that the best resolution exposures requires that the mask is cleaned between every single exposure. The masks themselves are also expensive and takes days, or sometimes weeks, to get. Using the maskless aligners are initially a bit more complicated, but requires a lot less technical skill from the user. The first step is to load the design into the software. Then the substrate is loaded in the tool. The substrate and the pattern is then aligned. The exposure is started. When exposure is complete, the substrate is removed from the tool. The maskless aligners have quite a few areas where they perform better, or with less skill requirements, than the mask aligner. First of all, they have alignment features which are simultaneously quite advanced and easy to use. This makes the alignment accuracy of the maskless aligners a full order of magnitude better than the mask aligner. Since the maskless aligner is also a type of projection tool, there is no direct contact with the substrate. It also has demagnification optics, which means that it is generally capable of producing smaller features. The digital masks are basically cost-free, at least if they are made using open-source software, and they can be changed on the fly, if necessary. This makes the maskless aligners exceptionally great for R&D environments, like the one we have at DTU Nanolab. On the other hand, these tools are complex opto-electromechanical tools, with quite a lot more possible failure points than the mask aligner. They also expose the substrate in small segments, which means that the processing time is usually significantly longer. Exposing a small chip may take roughly the same time, but exposing a full wafer may take 1, or even 2, orders of magnitude longer time. Summarizing the main differences between the mask aligner and the maskless aligner, we can say that the mask aligner works more like a photocopier, where the maskless aligner works more like a printer. The mask aligner requires physical masks, which are slow to get and cannot be changed, whereas the maskless uses digital masks, which can be changed whenever needed and potentially without any cost. The exposure time in the mask aligner is short, taking only seconds to minutes, while it is minutes to hours in the maskless. This is reflected in the fact that the mask aligner is often better for batch productions, where the maskless is often better for process development. The complexity of the mask aligner is low. It is basically comparable to a simple lamp, which is turned on and off. The complexity of the maskless aligner is high, with many complicated parts that need to work together in a tightly controlled way for the tool to work properly. The first and most obvious exposure problem most users will experience is giving the sample too low or too high dose. When the dose is too low, we call it underexposure. Underexposed resist areas tends to be slightly smaller than they are supposed to be. For a positive tone resist, one of the most prominent features of underexposure is that the resist film is not fully removed in the exposed areas, leaving behind a thin resist film where there should be none. This is almost always displayed in a quite colorful manner, as can be seen in this example, where the blue color is residual resist film which should have been removed. The actual color of the residual resist is determined by the thickness of the film. When the dose is too high, we call that overexposure. Overexposed resist areas tends to be slightly larger than they are supposed to be. If your pattern has very small features, they might disappear completely, or multiple small features close to each other might grow into one big structure instead. Specifically for the mask aligner, the most common problems we see are particles and proximity. The particles often come from a dirty mask. The downside of contact lithography is the contact between the mask and the substrate. Really good resolution can only be achieved when the mask and substrate are in really good contact with each other, which means that there is a very high risk of contaminating the mask with resist. This resist contamination creates a gap between the mask and the substrate and can also be transferred to the next substrate as particles. Proximity is usually introduced in the mask aligner unintended by particles or non-uniform resist thickness. Particles could come from a dirty mask as mentioned before, but they could also come from handling of the substrate. An uneven resist thickness is quite common when using thicker resist. Edge bead is a type of coating defect, which can produce quite significant proximity between the substrate and the mask. For the maskless aligners, we typically experience other types of errors. The first type of error is related to the digital mask. Sometimes it can be imported incorrectly into the machine control software, or the file can be created in a way that makes it problematic for the machine to convert it to image files. The next type of error is with the automatic focusing system, especially the optical autofocus system, which can have problems focusing on transparent substrates, or substrates with a highly reflective coating. The absolutely worst situation is with a transparent substrate that also has patterning with a highly reflective coating. The final type of common error on the maskless aligners is when the substrate has a large bow. This can sometimes be caused by oxide or nitride film stress. If this bow happens to be concave, as seen from the top side, the machine might collide the right head into the substrate during exposure. Needless to say, that is undesirable. For most lithographic work bigger than 1 micrometer, we have mask aligners and maskless aligners. For work between 200 nanometers and 1 micrometer, we have a deep UV stepper. For work between 10 nanometers and hundreds of nanometers, we have E-beams. And although technically not exposure tools, we also have imprinters. The resolution of these are determined by the resolution of the stamp and can work in all three mentioned size ranges. The UV mask aligner uses a 365 nanometer mercury eye line exposure source and produces features down to 1.5 micrometers. Processing on this tool is quite fast and can generally be used by all users, but is especially good for batch processing. Few UV maskless aligners have LED and laser light sources from 365 to 405 nanometers. Each tool has one specific wavelength, so it is important to select the correct tool for the resist you are working with. The processing time is a bit longer than the mask aligner, but it is far easier for alignment and reliably produces slightly better resolution. The deep UV stepper can have a very high throughput, but it requires that the process is designed correctly. The resolution on this tool is around 200 nanometers. The E-beams are used for creating features with the smallest possible dimensions, down to approximately 10 nanometers. This concludes the third lecture in the lithography TPT. Please continue to the next lecture, which is a more detailed look into the development process.